Introduction, and thank you all for being here and for remaining until the very end of the conference, especially in this beautiful day, so I promise I will be quick. So my name is Daniele Cirigliano, and I, together with my colleagues at the German Aerospace Center in Stuttgart, we are working at thermomechanical fatigue applied to combustion chambers of micro gas turbines. So a little bit of context, what do we do in Stuttgart in our department? So we design and develop new combustion chambers for micro gas turbines, and we perform structural and life analysis. So this is a representation of one of those components. And we simulate and test very different fuels, for example, classic methane, kerosene, so we also apply droplets combustion, and now also hydrogen is a very hot topic. And we instrument and measure in our labs the flames, and we measure the pollutants and so on. And there is also a team which plays a little bit with the components of the system, for example, the heat exchanger, the compressor, and tries different layouts. And we test everything. So my presentation today and my role in this department is the design of these components, so the numerical simulations. And my goal is to develop end-life analysis. So for a little bit of context, what is a micro gas turbine? It's a system for combined heat and power. So it basically provides electricity for small buildings and hot water, which can be used for heating as well as for sanitary hot water, let's say. And here you see two very typical German houses, so single family and multiple family houses. Those are typical applications for this technology, but it's not limited to that. So they are often found also in small hospitals and small industries and so on. So if you see the system and you take it out from the other components, it looks more or less like this. So here inside you find the compressor, turbine, and the combustion chamber in the middle, and the combustion chamber is what is the topic of today. So here you see it meshed in a numerical solver ANSYS, and when I say micro, it means that it's really small. So the thermal power is about 15 kilowatts, and the electrical power is also less than 3 kilowatts. And here you see also why they are called micro gas turbines. So this is the combustion chamber. This is the cold burner, so with 6 nozzles, and this is the size compared to a coin. And this is made of Inconel 718, and it's produced by additive manufacturing. The diameter is 60 millimeters, so it's very small. And in this case, we are burning methane. In one of these applications, as I mentioned before, you have a user who needs electricity and hot water, right, during the day. So here you see the time step during the day are 48 time steps. That means that every time step is half an hour. And the orange columns represent when the micro gas turbine is operating. And it's operating at partial load, so less than 100%. And when you don't see any column, it means that the system is off. So you see basically that when the system is on, you have an increase in the content of hot water, which means that you are producing hot water and electricity. Whereas when the system is off, you are basically using electricity. The users are using electricity and hot water. That's why they are decreasing. So this is a work that we extensively reported in a publication. Just to quick summarize here, in this use you usually have batteries for storing electricity and a thermal storage for storing hot water. So we see that these systems are constantly switched on and off. So they undergo many different cycles of work at different load points and for very different durations. So here is a representation only of half an hour functioning, but actually they can work much more dynamically than that. Here we see the temperature over time. This goes over 10 seconds. So we see that the hottest points in the combustion chambers are there where the flame is closest to the wall, and we can have very high temperatures and time-dependent temperatures. So since we have high temperatures, we have creep, right? So temperature higher than the half of the melting point mean creep. We also have thermal expansion pretty much everywhere, but many geometrical nonlinearities and potentially also different materials. Here we are only dealing with Inconel, but potentially there are different materials. That's why we also have fatigue. And the gases which flow inside and outside of the combustion chamber contain oxygen. That's why we have high temperature oxidation. So as my colleagues today already mentioned, with these damaging models, we have to take all of them into account if we want somehow to assess the lifetime of such components. One of the most used and common known models dealing with these three damage mechanisms is the Neo-Seitoglu model, which was developed in the early 90s. And it's a very complex model which models these three damage mechanisms, and we make the assumption of the linear summation of damages. So the total damage that you have is the sum of the damages coming from the three other damaging mechanisms. And the damage is the 1 over the number of cycles for each mechanism. And for each one of these mechanisms, we can model them numerically. So as you see, there are many material parameters which must be determined experimentally. We did not do any experiment in Stuttgart, that's important to say. We tried our best to find these parameters in literatures. And as you know, these parameters come from experimental data applied to probes, so to very simple geometries. And that's why the applicability to 3D large complex geometries is still to be assessed. The important thing that I want to tell you today is that we implemented these equations here in ANSYS Mechanical, using a user programmable features called UserMat, which must be programmed in Fortran, and that took us some time, some effort. And these equations here, with the material parameters, are solved in this problem at each integration time. So they are time dependent, and they are also spatial dependent. So they depend on the single node of your mesh. So it's a very complex problem. It's time dependent, and if you want to apply it to a large geometry, it's also computational intense. Today I will only discuss about creep and oxidation, only of these two terms. Here you see a comparison between our the creep that we implemented and some experimental data at different temperatures. And concerning oxidation, it's a complex model, and I will not go into the details. We see that the K, this parabolic parameter of oxidation, depends on temperature, and you can fit it here. Also, we have in phase thermomechanical fatigue, because when the combustion chamber is heating up, so you are going, say, from off, so the system is off, to 100%, you are heating up, so delta epsilon thermal is positive, but you will also have thermal expansion and mechanical stresses, so you basically end up always with in-phase thermomechanical fatigue. Here I reported just as an example what happens with creep. So we have the creep strain, which obviously increases in time, and the foam is the stresses decreases in time, and this can be attributed to stress relaxation. We see also that in our geometry, the areas more affected from thermomechanical fatigues are obviously those ones where notches are present. So those where large geometrical nonlinearities are present, and those are places which must be investigated more thoroughly. And concerning oxidation, these are just rough results, so we have to be careful with that. We see that the oxidation damage increase at the beginning because of this large thermal expansion, but then decreases. And these, we are still not sure about that, but they might be connected to the stress relaxation. So since the stress decreases, also the oxidation damage decreases. And still in this, so this thing is basically the small connecting part between the two, the cone and the combustion chamber. So summing up my conclusions, so we are still performing thermomechanical analysis in ANSYS with this user programmable feature in order to assess the lifetime of combustion chambers in micro gas turbines. The damaging phenomena involved are creep, oxidation, and fatigue. And the lifetime strictly depends on the boundary conditions of the system. So how many times is working, is turned on and off, how long, so half an hour, 1 hour, or just a few minutes, and potentially also the order of these working points. And finally, the geometrical nonlinearities are those hotspots which must be investigated at most. Yeah, I thank you very much for your attention.
Thank you very much. The paper is open for discussion, please.
I'm curious, you mentioned that you have used only literature for a set of very complex data. On the other hand, you mentioned that you have 3D printed material.
Mm-hmm.
So just have you managed to find all the data for this 3D printed material, or have you used the one for the bulk material?
Yeah, that's a very good question. Both. So sometimes you find material parameters for bulk materials, and sometimes you find literature, and people manage to measure experimentally additive manufactured components, and we got the data from there. In other cases, we just have to rely on similar materials. So you don't find, for example, Inconel 718, you find Inconel 725, and you take those, or other high temperature resistant nickel alloys. Yeah, that's a little bit of the drawback. And if I may add something, I'm also very curious about if we take these material parameters from the literature, from probes, can we really apply them to complex geometries? I don't know. I'm happy if you have feedbacks on that. Thank you.
Thank you very much. Any more questions or comments, please? I was wondering also about do you have already fracture surfaces and damaged components already?
Yes. We work in contact with some industries, aerospace industries, And so they are using combustion chambers for helicopters, for example. So they're not exactly micro gas turbines, but they told us, for example, that they have combustion chambers with very large cracks or even holes sometimes after thousands of hours, and they work perfectly. So.
And my question is related with the numerical simulations. Do the real damages verified in service coincide with your numerical simulations, with the most stressed regions that you found in the models?
We haven't done that kind of comparison yet. So our numerical simulations are not showing any crack. So we didn't implement a crack model, a crack opening and propagation model. But yes, we can definitely do that, and that's one of our future works.
Okay. Another thing that I was thinking, why to print those housings? What is the purpose? Is the series so small that allows you to print the housings? Why do you not choose another mechanical process in order to produce the housings?
Yeah, that's a good point. Yes, because they are very. It's still not a so widespread technology, so there are not that much demand for that, and that's one point. So these components are produced in small batches, let's say, and also because of the very small size. So due to this very small size, you have fuel inlets with the inner diameter extremely small, in the order of millimeters. And with this very complex shape. So to produce those with other techniques, I'm not an expert, but it might be challenging. So I guess that's the reason why those are produced by additive manufacturing.
Okay, thank you very much.
Thank you.
So thank you for your presentation.